No, sir.
Anyone else? Okay, so next we are going to move to how the propagator is related to the path integral. So I'm going to call this section the Markovian property. It's also known as the associative property, and sum over histories. So there are two ways in which path integral formulation of quantum mechanics is usually presented. One is Feynman's approach, in which Feynman was, inspired by a comment in Dirac's book, and then once we write down the Feynman approach, you can show that the path integral, implies the Schrodinger equation. Okay, so that's one way of looking at it. Another way of looking at it is that we assume the Schrodinger equation to be true. And from the time evolution operator, we derive the path integral. Okay, so one way or the other. So in most textbooks these days, people take the second approach because it's easier to understand. It's a lot of mathematical, there's a lot of mathematical steps, and the end of which you arrive at the path integral. But I think that it's instructive to know both. I think this is very exciting, the first approach. And so what I'm proposing is that, given that we have about an hour today, that I try to derive it according to Feynman's approach today. And in the next lecture, we do it in the other approach. Okay?
Okay, sir.
The path integral is very intuitive, but it's very subtle. And it doesn't hurt to see it twice in two different ways. Okay, so what we will do today that, without loss of generality, we specialize to 1 + 1 dimensions. Okay, it's very easy to generalize this to our dimensions. The other thing is that, let's start with the position eigenbasis. So we start with the position eigenbasis. And now suppose that we change to, the Heisenberg picture. So in the Heisenberg picture, the position operator, say x of t, it's a time-dependent object, right? And what we do is that we denote by the ket xt the position eigenvectors of the position operator at time t, okay? So I'm not saying that this is the t parameter is the time evolution parameter. It's not. I'm not saying that it's a that this is the time evolution parameter that we use in Schrodinger equation. Okay, so this can get a bit confusing because we are in the Heisenberg picture, and we know that in the Heisenberg picture, states don't depend on time, right? That the evolution of states, there is no evolution of states, right? That's not what we're saying here. What we're saying here is that these are states which are eigenstates of a time-dependent operator, and that's why we write t. Okay, so because, for example, if
Sir, does it mean that the eigenbasis will also change with the operator itself with time?
Yeah, exactly. So if you take the operator at a different time, say x prime, then you basically have, say, x at t prime, and then x t prime, right? So the idea is that these two states need not be the same. Okay? And that's why we have the time dependence here. So, this is the, so we are going to be working with these. So instead of, you can do it in the Schrodinger picture, but, it's just more convenient in the Heisenberg picture. So, of course, we should really be putting subscript h's here. But we won't do that because we'll be in Heisenberg picture, okay? So in the Heisenberg picture, well, what is the expression for the propagator? So the propagator is x, kxt, comma, say x prime t prime, and this is an amplitude, right? And we know that amplitudes don't depend on their pictures. So, but its expression in different pictures will look different. So in the Schrodinger picture, it was xu t minus t prime x prime. In the Heisenberg picture, this becomes x t x prime t prime, right? So this is the, hello?
Yes, sir. What is the second line follow?
Okay. So this is what the propagator looks like in the Heisenberg picture. Now, when Feynman was a young graduate student at Princeton, so Feynman was a young graduate student at Princeton and working under John Wheeler. He came across a cryptic, he came across a cryptic, or say a mysterious statement in Dirac's book on quantum mechanics. I was about to say on the Bible, but anyway. So, and what Dirac said was that the exponential of I by h bar times the action, which from T1 to T2, you can write as dt Lagrangian x dot corresponds to xt x prime t prime. Or sorry, I should use both, sorry, x1 t1 to, sorry, x2 t2 x1 t1. Okay, so this is a statement that Feynman found, that this factor, exponential factor with the action, with the imaginary unit multiplying it, corresponds to this thing. And Feynman wanted to understand, what did Dirac mean by corresponds to? Does it mean that they are equal? Does it mean that they are that one becomes the other in a certain limit? You know, what is a mapping? Okay, so this is this and a few other, you know, Gedanken experiments, you know, sent Feynman down the rabbit hole that gave birth to the path integral. So let's you know, do something. So let's use the fact that we can write the identity operator. We can take some time slice t double prime and take the state at that time. So this is our decomposition of identity in the Heisenberg picture. And we can then take xt, x prime t prime, and we can take t double prime to be a time that is between the final time and the initial time. Okay. So if I do this, then I can, you know, expand okay, so this is interesting because we see that we get an expression for the propagator in terms of two propagators, okay? And this property is known as the associative property or the Markovian property. Okay, so, well, I think they're kind of related, they're slightly different. So I call this the Markovian property. So what is Markovian property? Does anyone know? So Markovian property means that, suppose you have a system which has some state, the state of the system at, say, time n depends only on the state of the system on time n plus 1 times some operator, say. So in other words, the state of the system at time n, time step n, does not depend on state of the system in time step, say, n minus 2. Okay, so it doesn't have a memory of the state of the system beyond, you know, what happened just before.